Welcome to Ask and Learn.
So we have a complicated configuration of capacitors, but we can really just look at it in two separate parts. The first one consists of these 5 capacitors, like this, and the second one is just 2 capacitors. And then we take these two configurations and just connect them in series. So if we solve them separately, then we can combine them right at the end. So obviously the one on the right is much easier to deal with first. So each of these capacitors are 10 microfarads. So to combine them, we just add the 2. So they're both C2. So we get 10 microfarads plus 10 microfarads. So that configuration is 20 microfarads. Now for the left part, these two are in series, and these two are in series, and the whole setup is symmetrical. So I can just do one side and then mirror it on the other. The top capacitors are 5 microfarads, and the bottom is 10. So this capacitance, combining those two, well, they're in series now. So you have to multiply them and divide by the sum, which is 5 times 10, and divide by 5 plus 10. This gives 3.33 going on. That's microfarads. And now we just have a setup, which is 3 parallel capacitors, like this. So now we can just add the 3 up. Well, the 2 on the outside, those sum to 6.67. And then we add the one in the middle, which is 2 microfarads. Yes. So this whole setup is 8.67 microfarads. Now we're left with one big circuit, equivalent to the original picture, where we have one capacitor that's 8.67, and the other one is 20. And these are combined in series, so this is point A and point B. So they're combined in series, so the total equivalent capacitance of the whole circuit is going to be 8.67 times 20, and divide by 8.67 plus 20, and that is 6.05 microfarads. And we also know that this voltage, which is from A to B, is 60 volts. And we want to find the charge on this capacitor from the beginning. So, that's also this capacitor. And since they're all in parallel, we know that the voltage through this first capacitor is going to be the same as the voltage through that. So if we can figure out that voltage, we already know the capacitance, so then we can figure out the charge. Now I have to work backwards a little bit. So the charge on the, say, total, Q total, or the same as this first one has a Q, I don't know what I should call it, QA and QB. These are all going to be equivalent because we have a series connection of capacitors. So I can say that that's the total voltage times the equivalent capacitance. And that would be the same as multiplying the voltage through the first capacitor times that capacitance, or the same for the second one. But I know the information for the whole circuit. So this is 60 volts and 6.05 microfarads. So the charge is 363 microcoulombs. And now if we know the charge through this is 363, that's the charge on all three of these. So now we can figure out the charge on just the middle one. But first we need the voltage through that whole component. So the voltage, I'll say this is, I guess this is V1 and this is V2, which is the potential difference through this from here to here. That potential difference is the capacitance, which is this number, times QA, which is 8.67. Nope. This should be QA divided by C. There we go. I mixed around the equation, so since Q equals CV, V is Q over C. So take Q, 363, and divide it by 8.67. We get 41.87 volts. Okay, so now we know the voltage through that first configuration. So now the charge on capacitor 3, now we can multiply C times V. Is C3 we know, and this is, I'm calling it V1. Okay, so C3 is 2 microfarads, and V1 is 41.87 volts. So this is 83.8 microcoulombs. Now, this is a real pain of a problem, but if you just walk through it step by step, each capacitor at a time, eventually you'll get the numbers you want. As long as you understand how to combine different values, voltage, charge, and capacitance in parallel and in series, eventually you'll get the number you want.